Hello and welcome to Rudy Electronics Lab. Last week I've been reviewing a new signal generator of Siglent, the SDG1000X Plus, and in that review there was one thing that I really got puzzled about, because one of the main new features that Siglent has been kind of advertising widely, the pseudo-random bit sequence generator, didn't seem to work with any of the other lab equipment I had over here. Now, we had a discussion on that on YouTube, on the EEV blog, but I think that question was not fully answered yet. So I decided to get back the generator for my son yesterday and do some more testing on it and really try to solve this mystery. So the question is, does this generator create proper PBRS sequence codes or doesn't it? Now, to answer that question, I think we have to dig a little bit deeper into a proper understanding. What are these codes? What are the applications of these codes? Are there specific requirements from whatever source that I have to comply with? But we're also going to dig into the device. We're going to measure it. We're actually going to get the code out of the device and see how it exactly looked like. We're going to study its properties, and then we try to see if we can answer the overall question. So let's get going. First of all, the core question kind of was, why was this not generated, the generated code not recognized by my analyzers that normally do so? All my analyzers work with my various type of sources. So the first reason might be that the code is improper. The code is not meeting the required properties, whatever they are. It's not repeating itself. It doesn't have the right numbers of ones in the sequence or whatever. Secondly, there might be a kind of a timing issue with the clock of the data. Now, normally these type of codes are relatively tolerant to things like jitter and wobbling and whatever, etc. But maybe somehow, maybe the upgoing clock timing was exactly at the same moment as the bit change in the pattern or whatever. Could be the case. It could be just that the zeros or the ones or mark and space, as they're sometimes called on devices, are not properly recognized. There could be excessive noise, so there could be too many bit errors to start with. There could be padding being used. There are some generators that actually do not do the sequence of 2 to the power of n-1, so the famous 511 length for a PN9 code, but they pad that to 512, so you can easily transfer that all into hexadecimals, and you would have a repeating code in hexadecimals. While normal codes do not repeat at hexadecimals. So that sometimes happens. Now, we could look into that. Most of the things I think are covered or will be covered in this video, and I think the main question is really the question number one: is this a proper code? The timing issues I think are already checked out in another ways, the ones and the zeros and the noise type of property. But maybe there are other reasons as well. Now, what is a PBRS code? And let's first look at the number of typical features that such a code has. It is a periodic signal, so it repeats itself, and it's deterministic. It's going to be every time the same that's repeated. So it's random within one single frame, if you want to call it that way, or pattern, but then that thing exactly the same way is being repeated. It has a number of mathematical properties that should be met. And one of them is that the value of any of the elements is independent of the other values of all the other elements here, and it has specific specified properties such as its autocorrelation function. Now, this is not a video on mathematics. I'm not going to go too deep into that, but there are good sources on the internet on that. It should have well neutralized and balanced data, generally meaning that you have a similar number of zeros and one in the pattern in order to serve its type of purpose. It is supposed to simulate real-life traffic as closely as possible. So, for example, if we use it to test a telecommunications link or so, we want the kind of traffic that we can stress the system on something that could happen in real life. It should be challenging but also predictable stressor for this type of equipment, which also means that you can reproduce the code and the tests are repeatable that you are doing with this type of system. And it also has a well-defined frequency domain characteristics. And later, actually, I'll look into that. I'll get a spectrum analyzer and I'll look whether I can recognize the frequency domain characteristics that are to be expected. I'll go into detail later here. The thing is that you can find a lot of sources on what PBRS codes are, but not all the sources necessarily always agree on what the characteristics are necessary and which of them are sufficient criteria in order to call it such a code. And you also run into quite a lot of documents that are even internally inconsistent on that type of thing. So it doesn't seem to be a very clearly defined thing to start with, making our quest a little bit more complex today. What are the type of reasons why people use this? Well, first of all, I think it's to test the behavior of high-speed serial interfaces like telecommunications links or channels or whatever, and then you do basically bit error rate testing. Second is the evaluation of noise, dispersion and inter-symbol interference, so you can be using eye diagrams on an oscilloscope, etc. to do that. You could also use it for measuring bandwidth requirements, for example for PCB design, because it has a very well behaved and predictable spectrum properties, really sending out digital signals there, not merely noise. And it can be used for pure digital type of test system, but also mixed signal system, when you modulate systems in a certain way, when you use analog to digital converters, digital to analog converters, etc. And that's just a few of the type of applications. We go a little bit broader and look not only at the patterns I'm looking at today, but broader pseudo-random type of patterns. They're used in code division multiple access systems, like the gold sequences that we find in mobile telecom systems like 3G or GPS satellite navigation. There are application encryption in time-of-flight spectrography. There are all types of other type of codes, Kazami sequences, GPL sequences. So the field actually is much wider even of pseudo-random codes. But I'll be looking very particularly at the type of codes here for bit error testing and the type of purposes that I start with. Another feature is the code length. So generally speaking, the faster the transmission line that you want to test, the longer is the code that you will be using. And common type of codes here are the PN9 codes, the 11, 15, 20 and 23. As you see, several of them are prime numbers, and basically prime numbers are preferably, because if you use later mechanisms like scrambling and those are somehow can be broken up into the same numbers that are in your PBRS code, that is not good. So prime numbers are preferable here, but still the 20, for example, is a common one that you see implemented in devices, and the 15 also not a prime number. One important thing is that these type of codes always have a string of N1s, where in the case of PN9, N is 9. Why is that kind of important? It is important from the testing perspective, so we want to know how does a system behave if you feed it with a number of ones in a row, because some system may not be able to deal with that well. They might have something like improper AC coupling, or the clock regenerator might not work, etc. So it's basically to test if your system can deal with it. It's also a great way basically that you can lock with such a test signal on the other side of the chain, just by looking at the number of ones. We'll be using that feature in a moment. And we will also see that having all ones in a test pattern is very convenient if you create it with shift register designs. And actually we're getting right now to the shift register designs, because the linear feedback shift register is the most common way to create this type of signal. It's also known as the maximum length sequence. And here you see a very simple but proper representation of how such a code generation will work like. We got a number of shift registers. With every clock signal, everything shifts to the right, and the first register is being fed by some kind of algorithm. And here you see this particular code length of 9. This algorithm is an XOR of position 4 and position 0. Now, you need a seed. When you get it started, you need to feed the register with starting values. And the usual starting value is put 1 in each of the register. And then we get exactly the 9 ones for a PN9 code. Normally we also define a maximum number of zeros. And that is not only from the testing pipe of perspective, but also the generating perspective. Because once that we fill up here all these registers with a 0, it will continue to produce 0 forever. And we don't have a code anymore. So we should prevent that type of situation from happening. And anyway, in any case, we'll see that all the algorithms that are common to do this will never actually have all zeros in the code. It's always n-1 for the maximum number of zeros in such a system. In the last sheet, you already saw that it's created by kind of a sequence. We call that a polynomial. And what's actually happening is that the way that the shift registers are fed back. So we just looked at the situation where we got 9 shift registers, but here you see basically what is happening for all the different kind of shift register length, and for each of them we basically have a code that complies with it. Actually, in some cases there are even 2 codes. I don't want to go that much into detail, but here we see at least 1 code that can create such a sequence. And these systems also have a certain number of properties that are kind of well understood, depending on the number of ones and the number of zeros, for example. And the numbers of ones and the number of zeros should be identical or close to identical. And we call that the balance property. They're never exactly the same, because since our code is basically a 511 length for the 9 code, yeah, you cannot have the same, but we take 64 and 63, so we're being very close with. There also should be defined run properties, which basically say that all the number of runs, so that are the same bits in the sequence, should be defined in a certain way. So the number of times you got just 1 sequence of things, the number of times you got 2 bits in sequence, the number of times you got 3 certain bits in sequence, etc. That is all predefined. I'm not going to show them all in detail right now, but we call that the run property. Now, why is it so important that there are simple hardware implementations for these type of systems? Now, I'm looking here at one of the older standards of the ITU, still called CCITT at that time. Later we'll look a little bit more into the standard. But if you look at the cover page of this standard, you already see this is a standard that dates all the way back to 1968. So the idea was that it was also feasible to create these type of codes with equipment that was available already many years ago. And actually it is not that hard to implement in hardware. Here you see a picture which is actually available on Wikipedia, and as you can see here, people just use some simple shift registers in logic chips, and they can just make a even fairly long 31-bit code that way. So it's fantastic. I could build it myself, but I don't have the time right now to do that. But it shouldn't be much of an issue, really. The actual implementation of the shift reg is so simple that we should be able to do it in software itself, and pretty fast. I'll give us 2 minutes tops and we'll make together a implementation. So here we go. Here we got the way that the register works. So we got register position 8, we got register position 7, and I'm going to repeat that until register position 0. Okay, I'm going to give them a seed, and the seed is actually all ones. And then whenever there's a clock cycle, basically everything moves. So register 7 became what register 8 was, 6 became what 7 was, etc. And what was 0 basically becomes the output. And that is then the first output we got, and we're going to call it PRBS 001. Now we need to get what's feeding into register number 8, and that's an XOR of number 4 and number 0. All right, so he's going to show that as a binary form. So let's do if this form is equal to true, there's a 1, otherwise a 0. So now we get it in the 0 form, and we need this 511 times. So let us create 511 slots. Go a little bit faster, 511 slots, there we go. And now we simply repeat our code for 511 times. And let's use conditional formatting so we can easily see the results. So, stop the time. Here we got our PN9 code. So it starts with the 9 ones, and we had expected it. Goes all the way down. We can later look at it to statistical properties, and ends with 4 zeros. So this must be the PN9 code that we're looking for. And just to be sure, is Siglent using this type of code generation, using feedback register? Well, at least in some devices, as it does. I've looked into the manual, several of their vector network analyzers, the ones that you see here, and there they actually write themselves that linear feedback shift registers are simulated to generate a virtual PRBS. So it doesn't have to be in straight hardware, but you can also have a computer algorithm that is actually doing exactly the same thing, or you can maybe even store like the whole code sequence in a piece of memory and playback. The specific device that I'm testing right now, however, is silent in the data sheet on the exact implementation. But well, we see Siglent is definitely knowledgeable about how to do that with shift registers. Having the signal generator back here at home again, I want to inspect its PBRS signal a little bit closer to see why my analyzers are not recognizing its code. So I connected it up to the scope. There's going to be channel 1 for the PBRS signal, and channel 2 is going to be basically a clock that I generated with the second channel. I can move it around in phase relative to the other one if need be, but I don't think we need to do that right now. So let's go and inspect the signal a little bit more. So if I stop the trigger for a second, I see a pattern, and that, yeah, looks like something like a PBRS pattern could have looked like. So there's nothing suspicious about that. So what can I go and test now? Well, basically I could go and try to see if it has exactly 9 ones in a row, because that is one of the things that we know that a PN9 signal that this one is currently generating should be having. Now there's a relatively easy way basically to do that, because we can use our trigger here. We can trigger on the signal itself, and we can decide to trigger on a certain width of the signal. So currently my scope is triggering on a pulse wider than 95 microseconds, so it would only trigger on 10 bits or more, but I have 9 bits exactly, so I could do 85. So it should not trigger on 8, but it should trigger on 9, so microseconds. And yeah, we got it triggered, yeah. And we can also inspect that manually. There should be 1, 2, 3, 4, 5, 6, 7, 8, 9 ones in a row. Yeah, so this looks exactly like the signal that should be looking like. And if I go to PBRS 10 patterns, then I should have 10 in a row. He's also finding this. Here 11, I should have 11 in a row. He's actually triggering twice on it. So if I increase a little bit, that he only captures the 11 thing, so that is more than 10, right? Let's try to do it with the dial over here, more than 10. Yeah, then we get 11. So yeah, that's fine basically. The and let's put it back here now to 85 to test for 9 bits. So it does have 9 bits in a row. So far nothing suspicious about the signal being generated here. I also know that it should have 8 bits in 8 zeros in a row. So let's also test for that. That's fairly easy as well. I will go back to the trigger and just try it for a negative trigger. It's not triggering here because there's not 9 in a row, but if I want to test for 8, I have to put it slightly below 8, so 75 microseconds. Yeah, I got 8 negatives in zeros in a row. So far everything looks like good. There's nothing suspicious about this signal. So what I really want to do is trying to get this generator to give up its signal, that I can really see the complete bit code and inspect it further on a computer. I'm not going to try to hack the hardware or anything, but I'm just trying to measure what comes out of here. So what I'm actually going to do is try to use the parallel decoder of this scope. So we got serial decoders, most scopes have this, but this is the only oscilloscope that I have with a parallel decoder. And I'm just going to use the parallel decoder not to decode 16 channels, but to decode just one single channel here. So let's prepare for that. Let's go back here basically to properly picking up the sync signal here for the positive one. We're there yet. And then we have to select the parallel decoder, and actually it's here in the list of decoders. So we got a parallel decoder and a parallel clock decoder, and the parallel clock decoder is the one that we're going to use here basically. But in order to do that, actually we will need the digital logic channel interface here. It's a little bit too bad that Rodi and Schwartz did not implement this function for buses up to 4 as well, with just the analog inputs and the threshold settings, so people could do what I'm doing here today without actually having the logic channels. But this is only possible, and you only get to see it in the menu if you're digital. Actually, when I was trying to do this yesterday, I just couldn't find that function anymore, and I thought it was like removed with a firmware update or so, but of course that was not the case. I just didn't have the digital interface activated, so it was not showing up in the menu. Let's go and see. We need to configure this parallel interface, so normally you might configure 8 or 16 bits, or 15 bits in the case that you also need a clock. Actually, I wrote some comments on that in the compare document, but that's not the topic of today. I can set the right thresholds. Now, I took care of all of that. So we're going to decode a bus with just one single bit here. And if we are going back here, we actually see it's already kind of doing that. Huh? So we see here, these are all ones, 1B, 1, and then as bits, not at hex or whatever. Here's the 0. Here we see 1, here we see 0, exactly corresponding here to the values here. And in order to decode this as values as a total, we probably want to see the bus table here. So I'm going to protocol. I'm going to ask him to show the bus table, and I'm going to make the bus table a little bit larger. All the signals will get a little bit shorter. So here I'm basically getting to see the signal that I would like to see. Do I recognize, for example, this long string of ones here? It should be somewhere around here, but the easiest way to see it, if I would move it all the way, that string of 9 ones to the beginning of the screen, a little bit more even, and then I get 1, 2, 3, 4, 5, 6, 7, 8, 9 ones, then a couple of zeros again, a couple of ones. So I'm exactly seeing this code here. So this is basically what I want to save of the device. Now currently it is showing me 60 bits here, and that is because there are only 60 bits visible in the screen right now. I want once more, I want at least 511, so let me capture more bits. Yeah, 600, so now I got 511, so this should include at least a full cycle. So principally this should allow me to do what I would like to do, but ideally I'm going to capture a couple of these patterns in a row, so I can really test whether they are repeating patterns in the way that I would like them to be. I mean, the data is stable here, so I think it's kind of fine, but let me just go here to 1200, 2400. So we're capturing at least 4 entire patterns of 512 here. So that should be fine. So let me just save this to a disk here, and I can later look at it. And I'm going to call this PN09, and I call it A because I think I already have that file on my disk somewhere. So hop. Now going to inspect the output file for the oscilloscope into a text editor. This is BBEdit, my favorite text editor for macOS. It's a quite powerful tool. What do we see here? We see a preamble, what this is about. It ends with an OK code, and the actual data is here in the middle, and we see here starting with 0x, indicating that this is a hex code. So this is not the binary code we saw on the oscilloscope screen, but here expressed as hex code for what could have been a 16-bit bus. So if we're looking for ones, and that was the least significant bit, we should be looking here for a 0, 1. So if we're looking for 9 ones, then we should be looking for 1, 2, 3, 4, 5, 6, 7, 8, 9. And there we go, and we see that this pattern is repeating here, and it seems to be more or less the same distance in which it's kind of coming back here. So let me try to capture just one of these repeats here. It starts with this 0, and I think it went until here. And that is a repetitive pattern of 1022 we see on the bottom, which is exactly twice 511. So that's fine because we're seeing 2-digit here. I also see that everything is underlined here. That means that the code is perfectly repeating itself. So I was able to capture a well-repeating code from the device. All what is left to do now is take the hexadecimal codes and convert them into binary codes, only the ones and the zeros, and we're ready to inspect the actual sequence. It's time now to go and compare the different types of codes that we have, because we have the code that we generated ourselves with the algorithm. I took code from a variety of different other generators I have here using the same way of sampling them with the scope, and I got a Siglent code that I just measured. So let's go and compare these codes now. And I'm showing the results right here on the top of the screen. I'm not showing the full 511, that will be slightly too small, but the first 1 or 200 or so. So that what we see here in blue basically are the algorithm and 3 different measurement instruments, and they all are in agreement, they all produce exactly the same code. And then in green we got the Siglent code, and interesting, it's a different code. It also starts with 9 ones, but then it simply runs differently. I'm trying to look also into some of the characteristics of this code. I'm showing them here. Again, the other instrument in blue and the Siglent in green. So it's comparable or not the same in these characteristics. The number of ones is 256, the number of zeros is 255, so that's the same as the other instruments. The number of edges is 256, that's the same. The number of ones in one run, in one sequence, is 9, we just saw that. And I also double checked the numbers of zeros in a row is 8, so that's also the same. So these distributional characteristics are the same. Also, if I look at the distributional characteristics for all the possible runs, which I'm showing now on the bottom right, also in that respect the Siglent is similar. So with runs I mean the number of equal bits, similar bits in a sequence. So the number of times that we have a single value, it's 64 for both the ones and the zeros. The number of times that we have a sequence of 2 similar codes, it's all the same. Or 3 similar codes, bits, it's all the same. So all the distributional characteristics that we see here on the screen are the same, similar, but the code is not identical. And apparently that is why the code is not being recognized by any of my bear testers. In the beginning of the video I also said something about the spectral properties of a good PRBS signal. So also going to take a quick look at that. So I set it up here with a spectrum analyzer, and we should be expecting a sine x over x response for a pulsed waveform. And also with zeros at the multitudes of the clock frequency. Clock frequency is 100 kilohertz still. Going to turn it on here. And yes, this is exactly what we're going to see, a sine x as over x. And if I use my marker, I'm going to set marker 1, and I'm going to find where it is. The first low value around here, yeah, so that's 100 kilohertz, and there's another 200 and 300. So that's nice. We established that the frequency domain output of the Siglent is, yeah, what you would expect for a PRBS generator. Another spectral property of the PBRS signal is that the line spacing between the components that we see should be equal to the bit rate divided over the total sequence length. So let's test whether we can also observe that. So I got it at a bit rate of 10 megahertz. The sequence is 511. So if we divide that, then we should expect the line spacing at 19.5 kilohertz or so. So I'm looking at a very narrow part of our spectrum from 45 megahertz to 45.1, and I do see here these lines coming in of which the spectrum plot is made up. So let me just look at the marker here, and let me create like a first marker, and let me put it here at one of the peaks. Well, there we go, and let's create a second differential marker. And look at the peak just next over here. There we go, 19.5 kilohertz. So indeed with the Siglent we also do get all the spectral behavior that we expect from a PBRS signal. Now all of this brings us to the question, are there rules? I mean, what should then a signal look like if we see divergence in signal? Or if you want, how shall these signals look like? And I'm using the word shall here because we're going to be looking at technical standards. And technical standards, if properly written, they will use the word shall basically to describe what you really have to do. And the word should is a little bit more ambiguous already, at least if we look at what nowadays is being considered proper writing of technical standard. And what technical standards that I'm writing about? Now, the technical standards that are relevant here, you see all the time being referred to in documentation of equipment, are those by the ITU telecommunications sector. So the international body is actually part of the United Nations, and an ITU-T in the past was known as CCITT, one of the oldest standards bodies in the world with a history of over 100 years. And we're looking at the particular series of standards that are really about this type of code sequences, and it's their recommendations in the O series. And you got the 150 and the 151, 52, 53. We only really need to look at the 50. That's the overall document, already contains everything, and the other one basically describes in what situations you apply them. So I'm going to focus a little bit more on the 150 recommendation here. Now, unfortunately, I don't think it is very well written. I've tried, as honest as possible, trying to make my own reading of what are the requirements of the standard, and what I can find as hard requirements would be that we would need to have a length of 2 to the power of n minus 1. Well, I think we already all know about that. That a regular type of sequence, and regular means here non-inverted, should have a maximum string of n consecutive ones, so there will be 9 in the case of PM1, and the maximum number of zeros of n minus 1. And I think they mean to say there should only be one string of that length, but even that is not very clear. And we also understand from the standard that there can also be inverted codes, and they have exactly the opposite properties. They're just simply inverted. Now then, the standard goes on and actually provides us with all the polynomials that already talked about this before. This is text that I'm just taking from the standard. It's just explaining that you can make a PN9 code by taking the 5th and the 9th stage output of a shift register. That's exactly what we just saw before. We can see how to make a PN11 code and all the other type of codes. And again, all these type of polynomials will result in a predetermined code. It cannot vary. Once you start the shift register with all ones, and then you start giving clock cycles, it would always come out with the same pattern. There's no deviation with it. All predetermined in this way. But now, looking a little bit more critically at the text, do you have to do it that way with the shift registers? Actually, it's a bit more complex, because actually the standard says that sequences can contain any possible combination of 0 and 1s within the string length dependent on n. So it's a bit more flexible. We can do it with shift registers, but apparently other combinations are possible as well. I don't know if I'm very happy with this definition, but it basically means as long as you have the requirements of the 9 ones and the 8 zeros somewhere, a code that is all the way like ones with only 8 zeros in between seems to meet the code as well, technically speaking. I mean, it's not a very useful code, but technically it seems to comply. The text also says pseudo-random sequences may be produced by means of a shift register. So apparently they don't have to be. And actually in another sentence we also see it's possible to make sequences with these properties by other means than shift registers. So it's clearly saying that shift registers are not the only way to create such a sequence. At the same time, a little bit higher, it also says that the properties of a test sequence should meet the requirements of the system on the test. And yeah, that's a little bit of a difficult requirement in the standard, because these type of, the system on the test might differ, and you have to comply with that, but what it is and how it complies, the standard doesn't explain that. So yeah, it's a bit of a difficult standard. I hope nowadays, and I would say nowadays, standards are better drafted than this standards. We too often see a bit of vague language and ways you can do things, and not being clear what are hard requirements or not, a little bit of inconsistencies. Yeah, I'm not very impressed by this standard, but by any means, this is the thing we have to look at. This is the thing that everybody kind of refers to. Now, coming to an overall conclusion here, I would say the SDG1000X Plus, as been testing it last week, does produce a PRBS 9 code. Because as far as I can see, it complies with the ITU standards that I've just been talking about. Having that said, you know, these standards are not very useful in the sense that almost anything can comply with that. Also type of test signals that are completely useless, but technically speaking meets the standard. Now, the Siglent SDG implementation goes one step more, because also its other properties, as we've seen in these videos, are similar to those ones created by shift registers. So the balance property, the run property, all the sequences that can appear, the spectral properties, etc. They're all kind of similar to what I find in all my other devices. But, there's a but, similar is not identical. The outcome of the Siglent is not identical to the linear shift feedback shift register that I find in all my other devices, and which is also expected by all my testers. So all my other devices produce shift register type of codes, all my testers expect that type of thing, and the patterns generated by the Siglent SDG basically are not recognized by any of my testers. Now, I don't have that many testers, but it seems that everybody kind of implements that meeting the type of test equipment that you make in the ITU standard really is about implementing a feedback shift register. Now the big question is why? Why do we find this similar but not identical code in the Siglent? I really don't get it. It is not hard at all to make the what I would call proper type of code that would work in the lab environment. It wouldn't take them any more work or whatever. Where they got this code from and why they decided to put it here, it's also completely undocumented what code is there, and if there are any qualities there that other codes don't have, then please tell us so. But we got no information whatsoever. So I would really appreciate if they would update their firmware of their devices and simply implement a shift register code that will work with any of the other lab equipment. And actually they do already do so in their signal, their VNAs. So it's not something unknown to Siglent. This is something that the whole industry basically does use the same type of code, so you can use it with other devices, and I think it will be really great if there will be a firmware upgrade that Siglent simply does the same thing instead of using another non-identical code, which I think is just creating some problem for people. Well, that's my take on it. Thanks for watching. It became a pretty long video because the question was more difficult to answer than I thought it was. But I hope this helps to get a little bit of an understanding how this device cannot be used. And let's watch out. And some people already commented that they were feeding this back to Siglent. And yeah, let's see if we get any firmware updates on this. See you next time.